Welcome to the course Algorithmic Design. So I'll first open the tutorial and I'll just show you what the result is, and then we will go kind of step by step. Okay, first we will do this load height map. Okay, so this is the code, and again I will explain step by step, but I'll just change a little bit the preview here in Rhino. I don't like this grid actually, not a big fan of grids. And I might go, I'm not sure if I go from white to, again, this a bit grayish, maybe a little bit of gray. Okay. Okay, and if I run this, I should get the height map. Okay. So this code called load height map, it basically just loads an image that we have in the folder, which is, I'll just find a folder. So you need to have this image in the same folder. It's called field mountain high res. That's just a PNG image. So that's basically that is the image that from which we are reading the height map values. And specifically here, we decided to say black is the low part of the terrain, and white is kind of the high part of the terrain. And then of course we have gradient in between. And what we do, we sample this image, and for every pixel or every second pixel, depending on the density that we decide, but basically for every pixel or every point where we decide to sort of sample, we can put a point in Rhino, and we can offset this point in height depending on the depending on its grayscale value. That's it. So that's what happens here. That's what's happening here in Rhino. So if I go from the kind of top, you can basically see the same image. It's the same image because it's not only that we offset the point, but we also color it according to the image. Or so the high points are actually white, and the black points or the low points are actually black. So it gives this also kind of additional reading. So if I go here in Rhino, you can kind of sort of fly through it. And this is a point cloud. So you cannot really manipulate the individual points here. We would have to explode this point cloud in order to, well, I guess you can manipulate, there's some kind of point cloud functions where you can sort of delete points and so on. So you can sort of manipulate a bit the point cloud, but the idea is as long as these points are batched up together, this is a very fast preview. But if you explode it and these become individual points, then they also become a bit uglier. In Rhino, they become kind of thicker, plus it becomes harder to, like, everything just gets slower. Okay, and this code is rather short. So I will actually open a new file, and I will try to recreate this. And the way I will do it, I'll just open a notepad. So I'll just run you step by step through it. It's not very long. I'll open a notepad, and I will actually load this load height map into the notepad, and I will have it on another screen, which is above. Okay. And I'm back in Rhino. Okay. So I'll just leave this. I will leave this height map here while I'm writing the code. Okay. So again, standard. We have to import libraries. Import rhinoscriptsyntax as RS, and import rhino.geometry as RT. So that's RhinoCommon. And then actually, we need a few more things. We need something called script context. And this we use just once or twice. So we don't rename it, we just leave it as it is. So that library we need, and we need at least one other one. So system.drawing as SD. Now, also this is something that is probably different on Mac. I'm not sure. So I didn't test it, but this might be different in Mac. And if you, for example, want to use this in Grasshopper, this might also I think it's we have to use it somehow differently. But this is this system. This is basically your operating system, or so your operating system, which in my case is Windows, but again, depending on the operating system you have, it might be something different. It's common that the operating system gives some like common functions that you can use. For example, then you can write code that you can use the operating system to access, for example, images or sound or something. Also, these are then system specific, but somehow I think this is basically, yeah, the idea is basically to kind of, this will enable us to load images using basically Windows to load an image and then, for example, get pixels and so on. And I'm not sure how universal it is. Again, it might work in Mac, but to be honest, I'm not 100% sure. But this is basically not Rhino specific. This is like operating system specific, and you can then use it in different programming languages as well, or to access images. Okay, so I'll save this just as today's date, 21/03/23, and I'll call it, yeah, I'll just call it load height map. Why not? Okay. So if I just run this, you can just run it to see if the libraries load correctly. If you don't get any error, then it's working. Okay, and I'm not sure if I did this last time, but we're going to use a neat trick to always, every time we run the code, I want to basically delete everything that is on the canvas, or I want to, for example, purge default layer. If you remember last time, we would always select and kind of delete in Rhino, or we would do, Control Z. But maybe I want to do this over code or so. Again, I don't really remember if I did it last time, but so I can collect all the objects in the default layer by using objects by layer function. So rhinoscriptsyntax has a function called objects by layer, and there I can get identifiers of all the objects that are in the default layer. And these I'll then call objects. These are some objects in the default layer, and then I can say rs.delete objects. So I have to use the plural here. Okay, so don't be confused, I'm using the same name. Objects here, small letter, small capitalization. Here's this big capitalization. I can call this whatever I want. I can call them, identifiers, but these are basically then identifiers of all the objects that are in the default layer. And if I run this, you will see that my default layer is now empty, or so I basically just delete at the beginning, I delete everything that is in the default layer. So I don't have to kind of delete manually. Okay, so that's usually what I do at the very beginning to purge the layer. Okay, and now we will load the image. So I can say, well, there's some image object, and I can use, again, this system drawing library, sd dot, and the object is called bitmap, sd.bitmap. And I have to give it a name. I have to give it a name for this, of this file. And the file, so if this is a Python file, and I don't give it a specific path, but I just give a name, then the Rhino will assume that the file is in the local folder. Or so I just take this, the image of the name of this image, and I just paste it here. So again, as there is no other path, then again, Python will just assume that this is in the same folder. So if I run this, I should not get an error, because if I get an error, that means that maybe the file is not, named correctly, or it's not there, or there's some other reason. If you put the file inside a folder, you have to usually do this tools reset script engine. So if you do any changes in the folder where this file is in, then you sometimes have to run this reset script engine. So for these changes to be taken into account. Okay, so now we loaded our image. Now this image is, this is now just this bitmap object, or so I can just say, print image, and you will see that this is just an object. So it says here, it's a system droid bitmap object, and this is positioned in the memory, and that's it. So I can kind of, I can just use it now. Or so
one question.
Yes.
So in Mac, it doesn't have all the options you have, like file, or some of the options, like the reset thing. Is there a way to do that manually by by typing?
You mean this one here?
Yeah.
Yeah, I don't know. So it could be that. Are you sure this doesn't exist in Mac?
I don't have. My Rhino hasn't opened yet, but yeah. I don't think.
Okay, but look. So this you don't really need to run. I mean, it's if it works without running this, then it's fine. So this you only use when, for example, if I would now go into the folder and I would put an image in, I would put something else in this folder. And if I would go back here and try to call that object, to try to access the object, Rhino might tell me this object is not in the folder, but it is, okay? It's inside, it's just that Rhino didn't take into account changes in the folder. So sometimes then it helps if you just reset. I'm not sure what happens if I do this and then kind of open it again. Sometimes that also works. And it's a bit of a, could be that in the Mac, this is just resolved automatically. So just try to run the code. And if it works, if this code works without running, this reset script engine, then don't worry about anything, then it should be fine.
Sure.
So again, I don't know exactly what, I don't have experience with the Mac version, but Mac is kind of Linux or Unix based, so some of these things, they work a little bit differently. They might even be easier. Okay, so this function now just creates an image object, and now this image object has some attributes. Has width, which is image dot with the width, and there's a height, which is image dot height. I just realized that in my code, I'm doing this, but I'm not even using then these variables. I just use directly this. So, but basically, I can with this, I can kind of now sort of ask. Right, I'm basically now storing. I'm storing the the width and height of the image. So if I don't know how big my image is, these two numbers will, or these two attributes will give me these numbers. Or so. I mean, I could have just used them directly, but here I just renamed them. Or so my picture is 500 by 500. Or so this I know, and this might be useful because depending on what I do with the image, it's sometimes, of course, useful to know how big the image is. So I have stored these two values. And now I will also create, I'll create a point cloud. Or so I already said that we will use a point cloud object to create this terrain. This is a point cloud. If I select it here in Rhino, it says here one point cloud added to selection. So I have to first create, point cloud is like a container. So I need to first create it, and then I can add points to it. So I say point cloud equals, and I'll use this Rhino geometry for that. So rg dot point cloud. And I just write it like this, which means this is now a point cloud object, but it doesn't contain any points yet inside. So it is just empty. So that's good enough for us for now. And again, you could use this procedure to basically create a point cloud and then add, if you have a model that has a lot of points, you can use this again object to kind of add to quickly draw these points. So you could do tons of stuff then with it. And it's really faster. So here we are using it just to create this terrain. Okay, that's it. And then there's one other parameter that I added, which is like a height scale. So this we'll use later. So here I just set it to some number. So my values, my grayscale values, they go from 0 to 255 on the image. So those are the numbers that I will get. But the question is that then the actual height in Rhino, or is the height in Rhino something else? So height is obviously proportional to this grayscale value, but what is the actual height in Rhino? To decide that, we can again just use the same number, or we can use a certain scale. So we are basically going to scale the grayscale value by this number, by this factor, in order to get the correct height in Rhino. Okay, so that's it. So basically, yeah, so that's just numbers we will use later. And yeah, and then that's it. Now we enter the main loop. So in order to sample this image, we will go by, this is X, this is Y, or we will call this is X, this is Y, and we will call this maybe I and J, something like that. And in order to go through that image, we need to create a nested loop. So again, 2 dimensions, nested loop. So we say for I in range. And the first range is basically, it will go from 0 to width of the image. And here I will add 1. And this 1 is actually, so I go from 0 to whatever the width is of the image, but in steps of 1. And this is like a step. So I want to give it maybe a good name, maybe something like yeah, something like draw step, something like that, or sampling step, maybe better. Okay, so sampling step will be 1. The sampling step just means that I will now draw basically every pixel. But if I put sampling step 2, it means I'll draw every second pixel. So maybe if I want to just do a quick test, I don't want to really work with this huge point cloud, but maybe I want to test it on a smaller sample. So I'm kind of skipping every second point, which for this surface will make, if I skip every second point, this will make everything 4 times faster because I will have 4 times less points. So I can kind of speed up the calculation if I'm doing certain tests, but maybe now sampling step will just put 1. So yeah, that's related to this range function. Range, I have start, end, and then the step. Okay, and then I have also, my internet is a bit slower. Hopefully you can still hear me. For J in range, and the same thing, but we are, instead of using width, we are going to use height. And yeah, again, I think in the example file, I just used, I used a bit differently. I used, instead of using this, I used this value here. So yeah, but it's the same value. Okay, so this is now going to be executed for certain number of I steps and certain number of J steps. And now we are in the main loop inside, and we have to decide what to do. So we are first going to grab pixels. So we can say pixel, there's some pixel objects, which will be image dot, and here, unfortunately, there's somehow no autocomplete, but it's get, it's called get pixel, ij. Okay, so this is a method of the image object. It's like an internal function of the image object. And this get pixel, I give it coordinates of the pixel. And then this pixel will be a pixel object, and it will contain information about color, for example, and maybe some other things like brightness and so on. So this is now my color. This is like an object that contains information like color, for example. Okay, and now I want to actually create a pointer. So for every pixel, there's going to be a point. So, do you want to reload? No, okay. So I can say, my point is rg dot point 3D. Okay, and point 3D will be, so the coordinates of the point will basically be I and J. So the same kind of indices that I have for sampling the image, they'll just be the same for the point as well. But now the question is, what is the height? Or so here, the height should be somehow related to the, the brightness of this pixel. And again, there are different ways to do this, but I specifically know that this pixel has an attribute called R, and that's the red channel of the RGB. Or so this is still a colored image, so it's kind of grayscale, but it's still colored, or it has RGB values, I think, because I don't think it's grayscale. But as you know, if you have a grayscale image, R, G, and B channels, so red, green, and blue, they're all the same. So that's this kind of diagonal of the RGB cube. The values are the same. So I can use I can use R or G or B in this case, and maybe there's something like brightness or something like that. But I'm not really sure. I would have to check. But basically, I'm sure that so the red channel is there, and this red channel is basically the grayscale value. And again, I can multiply then this with this height scale. So it's just going to be a number that will be scaled by this height scale. So this is a bit long, but it's just yeah, the grayscale value multiplied by this factor here, which will make everything kind of shrink a bit down. I can actually put the height scale here to 1.0, so you can see what happens when when the height scale is just 1. It will be a very kind of stretched terrain. And then later we can kind of stretch it back down. Okay, so that's my point. And that's it. I could basically just draw this point directly, but again, I need to make it a part of the point cloud. So I can say point cloud. That's now my object, point cloud object, and point cloud object has a function or method called add, internal function or method called add, which basically adds a point to the point cloud. And point is the point 3D, and then we can actually add, very conveniently, we can just immediately add the pixel. So this pixel object goes in, so it's like a color, and this point cloud will actually recognize this pixel object, and it will extract color from it, and this color will be then used to color the pixel in this point cloud, or this point in the point cloud. So that's very convenient. Yeah, it's very convenient. It's just like that. I think you can also add here, like just in general, I don't think you can add you would have to create, I can show you maybe later how to, you can create your own color, but then you have to use a separate function to create like a color object, and then you can use it as a color here. So you can just make everything, whatever color you like. Okay, and that's it. But this, if I just run this, and nothing will really, nothing will be drawn. So there's like everything is empty. And the reason is because when we create objects using Rhino geometry, so using this Rhino geometry library, the geometry objects are not really drawn in Rhino until we basically explicitly tell them to be drawn, or so we have to add them to the so-called objects table. Or so that's the difference between the RhinoScriptsyntax library and Rhino geometry, because in RhinoScriptsyntax we create the object and the Rhino will automatically add it to the objects table. That's why usually the function is called something like add point, or add line. So it's adding it to the canvas, but basically adding it to this object table, which Rhino uses to draw objects. And here these two things are separate, so we can create an object, but then it's not really drawn until it's added to the objects table. So for that, we need this script context. I'll just copy paste it from here. It's a bit long. I was always looking how to do this shorter, but somehow never find a way to do it shorter. So that's how it is. Script context dot doc dot objects dot add point cloud. Okay, so this function will add this point cloud to the Rhino's objects table, and then it will be drawn in Rhino on the Rhino canvas. And if I run this just like this will, I think, already work. I can just test it. Yeah, so there's some weird thing is happening is if I run it, you can see now the execution finished, but you cannot see anything. And it's because we also have to separately run the redraw, or so the canvas needs to be redrawn to show for us to kind of see. So Rhino needs to redraw the canvas in order to show what's in the objects table. And this does not, again, happen automatically. This happens only when I change something in the canvas. So I have to kind of rotate here. If I rotate the canvas, the object will automatically appear. So that's a bit annoying. So I can do this redraw basically by saying script context dot doc dot views dot redraw. Okay, so unfortunately, when I'm using this Rhino geometry, well, fortunately or unfortunately, when I'm using this Rhino geometry, this RhinoCommon library, then some things that were before done automatically, like this redrawing, would be done in if I would use, for example, just add point or add curve in the RhinoScriptsyntax. That in the RhinoCommon, this is not done automatically, so I have to kind of call this function separately, which is of course great because I have more control, but there's a bit more code. Okay, now the code is complete. So if I run this, execution is done, and the object is drawn directly in Rhino. So this is how the model looks like if I don't have the scaling factor in. And because the highest peaks here are basically white, so this height is 255 or 256, and the lowest points here, which are black, are probably at 0. Okay, so, and I can check this if I go here under, for example, front. I can check the height of this model. Not sure exactly how, but you can see here down there's a number here. If I go all the way to up, I'm very close to 200. Well, I guess this 230 something, or so. That means this is maybe not completely white, or I have to say just a line 0. I guess I could also measure it somehow. Yeah, it is 230 something. So this is not fully white. It's a few shades, maybe 20, 30 shades below the full white, or maybe 15 shades below. And of course, this is now already okay. But if I want to make this terrain look a little bit nicer, maybe not that hilly, then I can use this height scale here. And maybe I can, if I put 0.5, I can just scale it down by half, and maybe this is okay, but maybe 0.2 looks even nicer. So basically what I'm doing, I'm scaling the whole terrain by, I'm scaling it in Z, or that's it. So yeah, that's it. So I basically recreated the image. I recreated the image using the height map. And that's the whole code. And just to show you how universal this is, let's use a different image. Funny enough, I don't really have an image prepared, but I will try to maybe find something, maybe under here, temp. Let's find something. Yeah, you can use any image. Actually, let me just think a little bit. Did I use something? Okay, let's find something online quickly. So, object Marlon Brando. So let's find the image of Marlon Brando, one of my favorite actors. Maybe this one here is super nice. Okay, save image, and we will save it here. So again, it can also be a colored image, but in this case, it's maybe convenient to just use black and white. Okay, save, goes in. Now I have it in the folder, it's here. So this is some image, and it might be a little bit too big, so we can kind of, we have to be a bit careful. So I can, for example, just take this name, go into my Rhino, and I have to go here again, reset script engine, and I can just put the name here. And maybe I would have to sampling step, maybe I skip every 5th, or I just do every 5th one because I think this image is quite big, so I don't want to clog up, but we can increase this. Okay, now I will do the same thing what I did with terrain, but I'll just pretend like my Marlon Brando image is a height map. So if I just run this, I got it, here it is. And it's a little bit, yeah, let's actually put sampling step maybe 2. Okay. Yeah, that's it. So if I go from the top, okay, it's kind of flipped because, okay. Yeah, that's one. Okay, so it's flipped, and I'll explain you why it's flipped. But basically, this is the result. Also, the dark areas of the image are low, and the light areas are kind of high. Yeah, that's it. I can kind of use now basically any image to sort of create like a terrain. And there's a reason why this is flipped. in order to correct this, I have to do this. I have to say, when I'm creating my point, I have to kind of flip the image. So I have to mirror it along the x-axis. And I do this by saying here, height minus j. Okay, so my j will be sort of flipped. It will become kind of minus. And if I run it now, I will get correct image. And I will explain why this is so. It's because it's this funny kind of historical thing that in the CAD environment, so in like, you know, from René Descartes and in mathematics and in kind of sort of a CAD environment, like AutoCAD, Rhino, and so on, we are used to having origin of the coordinate system on the bottom left. And you can see here a small Rhino, this small coordinate system. Also on the bottom left, we have the origin, and the y-axis goes up and the x-axis goes right. And again, this comes all the way from Descartes, you know, Cartesian coordinate system. This is how it's defined. But funny enough, when the first TV displays came in, somehow this oscilloscopes or this kind of electron beams, they would reconstruct the image. You can see how my mouse goes from the top left down. This is how the image was recreated on old TVs, for example. And I don't really know exactly why this was so. Somehow the image was drawn from the top down. And because of that, today's screens, the origin of the kind of screen is not bottom left, but top left. Okay, so when you work with, for example, in processing, and when you define images or kind of coordinates of images, and also, for example, for JPEG images and so on, that you basically start in the top left. And this, again, in my very limited understanding, this has to do with the fact that kind of how images were created in a digital way, kind of decades ago. Okay, so the start of the coordinate system is top left. Also, if you do web page design, if you do like web pages, you know, like maybe HTML5 or JavaScript, there you also kind of, when you draw objects, you kind of imagine as if you start on the top left, or and then the objects, when you add the positive y, they kind of start going down. And because of that, we kind of have to flip. We have to flip this y-axis here. Okay, so that's the only reason why that's so. Otherwise, everything is kind of flipped. It's sort of inverted. Okay, I will actually conclude this example. I will actually go back to. I will go back to the height map here. So I can just copy paste this name again. Go back to height map. And I will save this. And now actually also we should have this flipping here, because now when I reconstruct my terrain, now this image that I have, it's the same. It's matched to the image to Aalto. These two are the same now. This image is correctly, it's oriented the same way as in the file. Okay, so I will actually run the example is this flow down gradient. Flow down gradient, and yeah, as you can see, it's a bit long. Yeah, it's very, very long. Basically, I added try to make it bigger. So I kind of had to I added like this and this and this, and there is probably a way to compress it, but unfortunately, as I said, I didn't really find a way to do it nicely. But the rest of the script is, well, this is basically the script that we had. And then the bottom part is kind of added. So it looks very long, but there's, again, quite a lot of repetition. Okay, so let's go through this. And I will just save it as a new example, and then maybe we can also compress it a little bit. So today's date, 21/03/23, and yeah, it's this flow down gradient. Okay, and let me just first run it so you see what's happening. Maybe we reduce the number of particles, so to 1000. I think it should work. So basically, we randomly distribute particles on the terrain, and then we let them flow down. So we let them kind of follow the steepest descent. And I will also kind of draw maybe do like a quick drawing now to explain a little bit what's happening. So yeah, these are kind of these are like little smudges, which are a bit hard to see, but I will try to show you. I'll try to show you a picture. I have a nicer picture where I did a big example yesterday. So I didn't give you these ones, unfortunately, but I can give them also. So it looks a little bit like this, or so when you do a lot of them. So basically, there's a terrain overlay, maybe like this. Yeah, there's kind of a terrain overlay, and basically these particles are they're shown here as polylines, so they kind of go down, and then yeah, they basically start following terrain down. And even here, because this is like a tilted image, you can see it a little bit already. Kind of you can get the feeling of the kind of how sloped terrain is. And if you remember the image that I showed in the presentation at the very beginning, one of the structures, they looked exactly, I think, like this. Yeah, kind of the, okay. But of course, what happens with erosion is that particles flow down, or water flows down, and it's then also carrying away the terrain. So it's actually modifying the terrain as the flow is happening. So that's how erosion happens, and that's how these structures then really kind of appear. This is just sort of simulating water flowing down on a terrain that is not changing. Yeah, and again, here in Rhino, we have basically the same thing. It's just have a lot less particles. And so this is, for example, a line here. Yes, you can kind of select it a bit. Okay, so we start from some random point. It's this one here specifically, and then the particle kind of starts sort of flowing down. Now you can also notice, unfortunately, it goes down to this channel and then it kind of gets stuck. And unfortunately, I noticed this only yesterday, that all these particles, they get stuck in these channels, so they're not really moving further. And the reason is probably because it's again hard to see. Also here, they kind of come to these sort of bigger channels, but here they go down, but then here they're not going down anywhere. So this is of course not realistic, and I think it's happening because again, if I go to my height map, I have to switch a bit between things. If I go to my height map, probably the reason is because the grayscale values in these channels, like here, they're all the same. So this is, for example, black, and it's the same black. So when I sample pixels here, it's the same number. So there's no gradient, so this is completely flat. So the particles, when they kind of reach this, for example, black area, they stop because locally there's no gradient, there's no inclination. And this, in real life, of course, this doesn't happen because nothing is completely flat. And then it's, of course, when you have a lot of material, so a lot of kind of water, it cannot occupy the same space. So it starts sort of pushing each other out when the water is kind of draining. So due to sort of amount of water, the fact that kind of water is a physical thing that sort of, it cannot occupy zero volume. It has some volume that it needs to occupy. So it basically starts kind of filling up even the flat areas. That's the idea. And then eventually starts flowing further and so on. So here I couldn't really simulate, because we are not simulating water amounts. We're just simulating direction. Unfortunately, we get stuck in these areas that are maybe they're flat, basically, according to our model. So yesterday I couldn't really correct that quickly, but I want to now just draw for you. Let's see how that works. So I want to just show you what are we kind of doing. Also, there's a pixel. Aha, great, perfect. Look at this. Okay, so I'm doing. So there are these points. So we have a grid. So those are my grid points. This is amazing. Okay, I'll just do a few of these. Okay, that's our grid. And now we are looking at one draw. Okay, this one here, perfect. Okay, now we are looking at basically we are doing this iteration, or we are doing this for every element, or so. But we're looking, for example, at this point here. Basically, what we're looking at the neighbors of that point, immediate neighbors, and this is a rectangular grid, so these are the neighbors. We can, of course, define these neighbors differently, depending on the sort of effect that you want to do, but this is an approximation, or so it's only these ones here are neighbors. Or so this is our kind of the main point here. And then these are the, how many? There are 8 neighbors. And that's why in the code, you will see in the code, there are also, we always have this kind of 8, you know, we have kind of batches of 8 because we are counting the neighbors. Now, I didn't really name the neighbors in order. The neighbors just have like a bit random names. But for example, if this is my, you know, if this is X and Y, so that's my coordinate, then this one here is X minus 1, Y. I wonder if there's a way to draw. Okay. This one on the right is X plus 1, Y. Okay. So these are the coordinates of my neighbors. If my coordinates are X and Y, then the coordinates of my neighbors are X plus 1, Y, and on the left is X minus 1. And then I go on, you know, here is same X, but Y is plus 1. And here we have the opposite. We have X, same X, and then we have Y minus 1. So it is the coordinate when we look at this kind of X and Y, or so. And again, this is a universal way to label the neighbors, because this X and Y are variables, or so this is going to be some number like 50 and 60 or something. And then these neighbors, the coordinates of the neighbors will always be relative to the point that we're looking at. And of course, I'll maybe not do for all corners, but this one here is then obviously it should be X minus 1, and it should be Y plus 1. Okay, so we have this combination as well. And again, not to kind of do all the neighbors, but maybe this one here is then, what is this? This is X plus 1 and Y minus 1. Or so it's the opposite of the other one. Okay, and these two you can imagine there'll be what is that? This is X minus 1, Y minus 1, and this is X plus 1, Y plus 1. Okay, so this is how I define all the neighbors, and yeah, and you can kind of see a little bit that I have sort of basically all the combinations of minus 1 and plus 1 in R. So I'll just, let's see. Oh, I can maybe go. Okay, maybe I stop sharing my white screen. Okay, and start sharing my normal Rhino screen 1. Okay, so, and also, no, here's Rhino. Oof, I already thought in my head this disappeared. Okay, so in my code, you can kind of see a little bit that I have the same kind of thing. Or so I'm at one moment I'm defining. What is this? Yeah, I'm kind of, yeah, it's a bit kind of a mess here. So I'm defining the X of the neighbor 1, pixel 1, and the Y of the pixel 1. And I define it as basically the coordinates of this pixel 0. So 0 is that's the pixel that I'm kind of looking at. And then here I add the step size. So that's this one that I added. But I can basically extend this. I can have step, for example, 2. So I'm looking a little bit kind of further. I'm looking at neighbors that are a little bit further away. So this would basically be this one, or 1, and then this is, you know, x plus 1. This is y. Then I have x and y plus 1. And then I have basically all the combinations from pluses and minus are here in these 8 neighbors are defined like that. So it's basically in this part here. So the first part of this code is what you saw before. We just kind of created terrain. So that's exactly the same. We just kind of create at the very end, we have this script context add, so objects add point cloud and kind of redraw. And the new part is kind of here. So basically we start creating these particles. We say we have, in this case, 1,000 particles. We define number of steps. So we say maximum is 100 steps. Or so this line here, this curve will have maximum 100 steps. Maximum 100 steps, even though here it doesn't look like 100. But it could be that it's just kind of gets stuck at one moment, which is also weird that it gets stuck so fast, but so it is. So we have this 100 flow steps, and then this is this kind of step size. So we choose if we look at the neighbors that are +1 away or +2 away or something like that. Okay, then we have a separate loop where we iterate for every particle, or our particle, we just have a number which we call here p. I think this p we're not even using anywhere anymore, but this basically we say if we have 1,000 particles, we do this loop underneath for 1,000 times. Okay, so what do we actually do for 1,000 times? So what do we do for every particle? We first define a random position, and we do this by doing the, we get some random x and random y, and there we use the random library, if you remember from before. And random library has it has a function called randint, which it gives us a random integer. So if you just use, for example, a random.uniform, we will get a random float number, so a random decimal number between two numbers that we define. But if I say a random int, then I can define the minimum integer and the maximum integer. And this just means that I get a whole number, so an integer number, which then enables me to use this as a coordinate for the pixels. If I say here there's a pixel, let's say image get pixel, x and y, I need to use integer numbers. I cannot use floats. Or so when I'm accessing pixels, I'm not allowed to use decimal points. So I cannot say pixel 5.7. This makes no sense. Or so it needs to be an integer number, like index of that pixel. But it's basically this pixel that we get. So this part of the code here just gives us a random point somewhere on this terrain. Or so that's we imagine this terrain starts somewhere in so it is just randomly distributed. Or so one of these points will be chosen. And the reason why I kind of say here minus step size, it's just because I don't want these points to be too close to the edge. Actually, here somehow it is chosen, but I think it's only because if I look at the direction of this line there, yeah, it starts from here and then goes all the way to the kind of edge. But basically, I'm not choosing points that are kind of at the edge, because then I might get some issues when I get kind of to the edge. So I say we go from step size to width minus step size. So there's kind of a band in between, like at the edge where I cannot get a random point. So it's kind of a buffer area. Okay, but I get my pixel, and then I say, okay, now I have my particle, which is a point at that point. So I basically just I kind of create a point, like a particle point at that position. And again, I use the x. I use again this sort of inverted y to get, but it's basically y. It's just inverted. I have to subtract it from this height of the image. And I get basically the same height that I chose here for the terrain. Or so it's the basically this point is now this particle point is at the same position where this terrain point is, or that's where it starts. Then I create a particle path, which is going to be a collection of points that go down the terrain, and I append to it the first particle already. And I basically say I kind of this px and py, I just rename them as px0x and px0y. So in Python, you can do it like this. You can kind of, you can imagine it's a bit Python syntax, so you get to learn stuff. You can imagine it like this. So it's almost as if I would say this is the same as if I would say this equals this. Actually, yeah. So this is like a small tuple. Okay, I'll delete these ones. So in Python, you can actually use this a bit shorter syntax if you're assigning multiple variables or so. So I can either write it like this with comma in between, or I can do this and then this one here. Or so I'm basically assigning, the left one to the left one here and the right one to the right one here. And I can actually put as many as I want, or I can put again some kind of z, and here also some kind of z. Or so I can kind of bundle these variable assignments in Python by kind of one line by using this syntax. So that's just a little bit extra. And I do the same thing. Yeah, I hope this didn't confuse you. I'm doing the same thing here. Or so this value will be assigned this value here, or this variable will be assigned this value here. Okay, so yeah, I don't really want to confuse you. So I will encourage you to have a look at this code a bit on your own at home, but I'll just go a little bit quickly through it. So to explain what's sort of happening, because I think there's no point in, I cannot kind of, I will not write this from scratch, and I think there's no point in kind of going sort of really step by step. But basically here we assign the X and Y coordinates of the neighbors. So we have 8 neighbors, so these are 8 here. Then this is just exception handling, unfortunately. So this part here and this part here is exception handling. So it turns out if I cannot choose neighbors that are too close to the edge, or if I choose a point that is too close to the edge, then if I'm choosing the neighbor, it falls outside of the grid, and then I get an error. So I have to avoid this, and the only way I can avoid it is basically say if the random point fell at the edge, or if kind of one of these path points comes to the edge, then it just always gets replaced with the point that is at the edge. Or so then there's no error, because, for example, here we say if this x value is bigger or equal than the image width, then the x value will become the width. But here I will subtract 1 from it. I guess that was this. I don't know why I actually put this -1. But I basically snap it back to the edge. So everything that happens on the edge will be snapped back to the edge. That's the idea. So that's how I handle exceptions. And that's this whole part is just exception handling. The same thing from the other side, from 0. So if, for example, y is smaller than 0, so it's a negative number, it will be snapped to 0. So I'll just assign it a 0 value. So points that get to the edge, they kind of get stuck. They cannot move anywhere anymore, really. Okay, and then that's the important part. I get basically pixel value for every neighbor, including kind of the point itself that is examined. And I'm basically checking the grayscale there. I should have maybe drawn that, to be honest, on the whiteboard. Basically, I'm checking the grayscale value of all of these neighbors. And this code here is just basically checking which of these values is the smallest. So one of these pixels has the smallest grayscale value, which also that means that it's at the lowest point. And the next point that I will choose is going to be the lowest out of all of these. Or so if you imagine there's a point here, I hope you can see it on my screen. It's everything is a bit gray. Maybe you go somewhere down a little bit here where it's a bit darker. Okay, yeah, maybe here. So I have a point here, and I'm looking at all the neighbors, all the 8 neighbors, and one of these neighbors, which is this one here, has a it has a lower value, or it is darker pixel, and that's going to be my next point. So I'm going to make this particle basically move down or go to its lowest neighbor in that way. Also here I'm choosing which neighbor is the lowest, and that's it. I get this kind of a low point, which is x low and y low, and that's it. And then I assign it here to the particle path, and I now, in the next iteration, I say this low particle, now the low point that I got, this is now the next starting particle. Also, I will then examine in the next step, in the next kind of particle path, or for the next particle point or step, I will check what is then the next one lowest. Or so I'm basically tracking. I go from here, and I go down, 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 down. I'm kind of basically always choosing the lower pixel to go to. And of course, because I have only 8 neighbors, there's a lot of these diagonal lines, because I can basically only choose either orthogonal direction or a diagonal line, which makes this flow sometimes like it goes zigzag, or because the direction is not, I cannot choose every direction. There are kind of only 8 allowed directions. So my particle would sometimes zigzag down, for example, here, or where is it? Maybe here. It's zigzagging down because it kind of it is not allowed to choose an in-between direction. But it doesn't matter, because this polyline kind of also smooths out when I add this kind of curve. It kind of smooths out a little bit these points here. These are the control points, and then the curve is something in between. So it looks a little bit artificial, but it's just an artifact of it's because basically I'm not allowed to choose any direction, but I have to choose one of the 8 allowed directions. So there's certain kind of discreteness there. Okay. So again, there's probably a way to write this a bit shorter. This is just a long way that, but again, we are just choosing the lowest point and we move there. And then in the next iteration, we choose next lowest point, we move there, and we connect all the points together and create a line. And then we do this, in this case, 1,000 times. And yeah, this is a little bit kind of this sort of simulates the rainflow, or this is how this is kind of, if I would have a lot of these, maybe I can actually try to run it. Maybe I can have less flow steps and more particles. Let's see how that looks like. Hope my Rhino will not crash now. Okay, I generated this picture kind of yesterday because I knew it will take long. So that's kind of one example. Okay, it came. Okay, so it turns out that if I have a bit less flow steps, then everything is a little bit faster. So I can also hide, I can select this point cloud and just say hide. Okay, that's more or less the same that I had in the picture. Or so this is how kind of the water would run down. Now the next step here, if I would want to simulate erosion, I would say every time a particle kind of goes down, every time the particle kind of passes a pixel, at that moment, this pixel will also be lowered a little bit. You can imagine as if, when the water flows down the terrain, it takes a little bit of terrain off, or the little bit of sand or aggregate rocks flows down the terrain, goes into the river and so on. So that's basically what happens with erosion. Or so then these channels, these kind of paths would also start becoming like channels that would start kind of making the terrain go lower. And then additionally, as they go lower, they will attract more water, or there would be just more water flowing into these channels. And that's basically how erosion happens. That's how that's why kind of terrain starts getting these like natural terrain starts getting this kind of channel-like look, because there is a sort of a feedback effect, or the water is modifying the terrain, and the terrain is actually guiding how the water is moving. So yeah, then that's kind of how you get these sort of patterns that basically also appear here. And even though here we're not simulating erosion, but this is sort of already kind of a eroded terrain. Okay, but we could basically then go from a sort of a flat or very smooth terrain into kind of, we could just simulate eroded terrain. And when you work with procedural modeling, this is how these natural looking terrains are kind of done. Okay, I would actually finish with this example, because think I started babbling a lot, but you can have a look at it a little bit on your own. You can change, number of particles, number of flow steps here, maybe playing with step size, and maybe finding a bit better image for the terrain, because this is really a problem. I think that here we kind of get stuck. It's because the grayscale values, they become basically flat. So there's no flow here. So you would basically have to kind of tilt everything a little bit more to get these kind of channels so kind of converge.